And we'll round, so we fill the table, so we're going to draw the graph of the square root. So we're going to use the function x minus 2 and then take its square root, so the square root of x minus 2. Round answers to the nearest tenth where necessary. So this is negative 2 and the square root of negative 2 does not exist, but this is 0 and the square root of 0 is 0. This is 0.3 and this is 0.6 and this is 1 and the square root of 1 is 1. This is 2. 2 minus 2 and the square root of 2 is 1.414, etc. So 1.4. And this is 3 and that's like 1.7 something. And this is 4 and the square root of 4. So that's a nice point, right? 4 became a 2 when we took its square root. And the square root of 0.3 was 0.5 and the square root of 0.6 was 0.8, right? At least rounded to the 10th. And so let's graph the original function. We'll do this one in red. Y equals x minus 2. So we have 0, negative 2. Okay, so if I'm doing points, if it's a straight line, I like to draw all the points I can. What's going to happen? And throw arrows on both ends. Goes on forever. When x is 0, y equals x minus 2 is negative 2, and the square root of negative 2 doesn't exist, right? So those negative square roots don't exist. So we'll start here. So 0, 0. So that's right on top, same point. At 2.3, so that's about here, we have 0.5. So we'll go up to about here. At 2.6, it's going to be a little bit past 2.5. We're going up to 0.8. At 3, well, we're back, same point. If they're the same point, what's the fancy word for the same point? Invariant. At 2 and x is 4, we've got a 1.4. X is 5, we've got a 1.7. X is 6, we've got a 2. Okay, so this starts here, it's above, and then it's below. Okay, so having worked ahead, you've got the same stuff, right? So the graph of y equals the square root of x minus 2 exists only where the y coordinates, what does y have to be? What's the condition on y?
Positive.
Yeah, it's actually, because 0 is not positive. So it's greater than or equal to 0. Okay, so positive or 0. You could say non-negative. That's the fancy way of including 0. Non-negative. That's the positive and 0. The invariant points occur when the y coordinates are, okay, so when the y coordinate was, where are the invariants? Y coordinate of 0, right? It's invariant. So what's the y coordinate here? Y equals and 1. Because what's the square root of 0? What's the square root of 1? Okay. Invariant, right? Same value. So when the y coordinates are 0 or 1, then the square root of 0 is 0, and the square root of 1 is 1. And the invariant points here are 2, 0, and 3, 1. Now asking for points, ordered pair, parentheses, the whole deal, right? So 2, 0, and 3, 1. So questions have to be read carefully, right? I know on the practice quiz it said the x coordinates of the invariant points, or whatever it was, are. And on the your quiz it said the coordinates of the invariant points, or whatever they are. Okay, so it's slightly different form for the answer. So just read it carefully and understand. What are they asking me for? Do they want the coordinates of the point? Okay, then it's parentheses, right, and commas and stuff. Do they just want the x coordinates? between the invariant points, the graph of y equals root x minus 2, so the green graph, is that above or below the red graph? Above. So the graph of y equals 2 was above. Circle 1. Also the other. The graph of y equals x minus 2. Well, for the remainder of the graph, so for the rest of it, the green graph is now below. Here's one is below. So I mean, one is a fill in the blank, one is a circle below the graph of y equals x minus 2. If you think about that, why is that? Like, what's the square root of 1/4? It's a half, right? So square roots of numbers between 0 and 1 are larger than the numbers themselves, whereas square roots of numbers larger than 1 are smaller. Okay, so that's why here the curve is above, right? So when we get like 1/4 value of 1/4, then the square root of that would be 1/2. Graphs of y equals f of x and y equals the square root of f of x are shown and labeled, meeting the criteria, right? So we've got invariant points where y is 0 and where y is 1, right? So we want to look along. The line y equals 0 and just say where, okay, that'll be an invariant point. We want to look along the line y equals 1 and say that'll be an invariant point. We know if we're graphing the square root function that we're going to have to go above in here and then below, right? And we can take some actual values as well, right? I mean, so if I'm finding values for this, if this went up to 9, so I've got 4, which means that right underneath here it's going to be 2. Okay. Now, I mean, this was graphed by software, so it is graphed correctly. But if you're drawing your own graph, right, and you say, oh, there's 4, okay, then I'm just going to go straight down. There's 2. Oh, there's 9. Okay, I'm going to go straight down. The square root of 9 is 3, right? So pick numbers which are perfect squares. None of which was being asked here, but it's just observation. So what's the domain of f of x, the original function? So just x belongs to the reals, right? It's just a normal quadratic. So the set of all x such that x belongs to the reals. And what is the domain of y equals the square root of f of x? So where does the dashed line exist when x is -3 or well, it's not just -3, it's what is about it? So it starts at -3 and it goes that way, so how would we say that? X is less than or equal to -3. Okay? I mean, interval notation, it would be -infinity to -3 with the square brackets. But domain, we're using this. So set of all x such that x is less than or equal to -3. Okay? What else could x be? Greater than or equal to 1, right? So what is it? It doesn't exist in here, but it exists. And, close that off. Brace brackets are only used when you're doing a set, right? You don't use brace bracket as in place of parentheses. So x is less than or equal to -3, and we could, if we want, we could write in or. I mean, it can't be both. You cannot be both smaller than -3 or greater than 1. So it's one or the other. The function y equals the square root of f of x exists only where, and in this case, only where what is true about this? Well, let's not limit it too much. So where it's greater than or equal to 0, right? So it's going to be a number whose square root we can take, which is, what did I say it was? Non-negative, right? That's bad. But we just say greater than or equal to 0. State the range of y equals f of x. What's the range of this original function here? Greater than or equal to -4, right? So set of all y such that y is greater than or equal to -4. And what will the range of any square root function be? Non-negative. Greater than or equal to 0. Non-negative. I much prefer interval notation to this, right? So then it's 0, comma. So some tech. The invariant points occur when the y-coordinates are 0 or 1. It's like the third time we've done this, right? Repetition is good, but the invariant points rounded to the nearest tenth where necessary. So just reading from the graph. Invariant points. So let's just go left to right. So here's one here. So what's that point? Negative 3.3? Yeah, 2. Yeah, I mean, whatever. And so negative 3.2, 3.3, so I think it's closer to 3. And 1, right? Because it's points, right? It's the invariant points, coordinates, blah, blah. Where's the next invariant point? Negative 3, 0, and then 1, 0. And then what's the last one? 1.3 and 1. So our expectation for invariant points of the square root function is that the y-coordinate will be a 0 or a 1. Okay, to find those points, we just have to search along the line y equals 0, right? Because we know those points are on the line y equals 0 and the point y equals 1. When you were doing 1 over f of x, your invariant points could be the negative ones, right? Because it would be invariant, but we're not. That was last year. In general, the function y equals the square root of f of x exists only where f of x is greater than or equal to 0, right? So the function, the evaluated function, right? I mean, that's some function, you're going to evaluate it. You say, hey, that's got to be greater than or equal to 0. And, or that is where the graph lies on or blank the x-axis. So on or above. The domain of y equals f of x consists only of the values in the domain of f of x for which f of x greater than or equal to 0. I know, sometimes it's cryptic. The invariant points occur where f of x equals
0
or 1. The following is also true for the following values of f of x. If f of x is less than 0, the graph of y equals f of x does not exist, right? There is nothing. Does not exist, which in a future course will become DNE, because we use it a lot. If f of x equals 0, the graphs of y equals f of x and y equals f of x intersect on the x-axis, right? Because that's when y is equal to 0. So on the x-axis, those are invariant points. If f of x is between 0 and 1, then the graph of the square root is above or below. There's your two choices. Above, right? Because the square root of a decimal is larger than the decimal itself, right? Whereas the square root of any number larger than 1. So is, what do you say, above? If f of x equals 1, the graphs of blah and blah do what? Intersect. Okay. So let's be more, so they intersect on the line y equals 1, right? And that's the idea, right? If you're doing square roots, you just start saying, I'm going to start on the line y equals 0. I'm going to go along it, and anytime I hit the original function, I know there will be an invariant point. And I'll do the same thing on the line y equals 1. And again, wherever I hit the function, it'll be an invariant point. I know that between those two invariant points, my square root function will be above the original function, and then after that, it'll be below. Okay, so that helps you in sketching it, right? You've got those things going on. And when f of x is greater than 1, the graph is below. Okay, because in that case, the square root of any number greater than 1 is smaller than the number itself. Okay, so we want to just basically put all these together and sketch out some graphs. So for each function shown, accurately sketch the graph of the square root function. All right, so what are we going to do first? We're going to trace along the line. Which line are we going to trace along? y equals 0, or the x-axis, right? And then we're going to say, aha, and we're going to say, what about this? That is an invariant point. And then we're going to trace along, which? Y equals 1, and we're going to get here, and we're going to say, and if I'm going to sketch the line between these two, where does it go? It goes above. Okay. And now, I could just take the square root of some numbers, right? So, okay. And the numbers are going to be magical numbers which have square roots. So I can say 4, oh, that's going to be where? 2. And I say 9, that's going to be 3. That's pretty much an exact point, right? Because that's the point negative 3, 9. And we could work out the equation of that line. It's just a straight line. What's its slope? Yeah, 1 to negative 2x plus 3 or something. Right? But we don't need to work that out. We just want to sketch this. Okay, so we're going to start here. We're going to sketch above and then head this way, being below the line. Okay, and that's it. That's your sketch, right? What am I looking for? Invariant points. So you show me the invariant points, and that you have sketched the line above there. That might be a bit extreme. Okay, but it has to be above. Okay, try the next one. See what happens. Next one has a restricted domain, right? Between what and what? Negative 2 and 4. I'm not sure whether she shut off the egg maker. Hang on, I'm going to go see if somebody left. It's still online. So we go along 0. We got an invariant point at negative 2, 0, and at 4, 0. We've got invariant points as indicated by the green dots at like negative 1 point something. This is 4. So what?
2.
That's 2. This is 4. It's also 2. This is somewhat bigger than 4. It's going to be somewhat bigger than 2. How do I get from here to here? Just straight along the line? No. I need to go above that line. Right. Then below. Then come around here into the shadow. It's like drawing in an eclipse. I eclipse myself. I cannot see them. Okay, so what are we looking for? The invariant points, we're looking to make sure that the curve is above between the invariant points and below. And I'd look for these values, the 2's, right? And I look at this, I mean, you can't dip this down or anything. This doesn't have to be exact. You don't have to go sort of, what's the square root of 4.5? What's the square root of 4.5? 2 point something. Okay, so any questions? Line y equals, so Kate makes simple, right? You want to put down at some point, you probably want to sit down and just write out your own set of steps. If I'm going to graph y equals square root of x, then I'm going to do this, then this, and then this. Like, so I'm going to go along the line y equals 0, go along the line y equals 1, get the invariant points. I'm going to then go out whichever way. I'm going to find square roots of numbers that I can find, plot those points, and I'm going to make sure that when I go between the invariant points, I am above the graph y equals f of x, and in between the invariant points on 1, I'm below the graph y equals f of x. Okay. So what do? We go along y equals 0, and there's nothing there. So now what? Go along y equals 1. So there's an invariant point. Can I find any other points on this graph that I'm supposed to draw? Well, so when y is 4, I know that this is going to be 2. When y is 9, I know this is going to be 3. I don't have 16 on there. Symmetrically speaking, so how do I draw this? Where does it go above the graph? Isn't it supposed to go above the graph somewhere? It's in my rules. Only between 0 and 1. We're not going between 0 and 1, so we are not going above the graph, right? So it's just basically okay. So only between 0 and 1 does it go above the graph, and we are not going between 0 and 1 here. Next one's tricky. Do it on your own. You've got 25 seconds. Go. That's 24 seconds too many. Oh, you've taken 8,100 steps so far today. It's amazing. And most have taken place walking back and forth in front of this board. I swear it's inaccurate now. It's like it's got me as over 10,000 steps every day, and like I used to be in 322, and I was a lot further to, go see if the egg cooker is unplugged. Yeah, it was. That's what it was. Right? Well, first it would have buzzed, then the eggs would have started smoking, and then they would have burst into flames. What's the answer? This 1 point. That's it. There's 1 point on there, right? Just negative 2, 0. That's your entire graph. I can't do the square root of negative 1. Wait, that's a pun for anybody who knows the square root of negative 1. I can't do the square root of negative 1, but I is the square root of negative 1. Are we doing this? Algebraically determine the domain. So all we're asked is the domain. We're not asked to graph this. We're not asked to, just algebraically determine the domain. So what am I going to say? What's the statement that we're going to start with? No, I don't think we need to start with that. What are we going to start with? What do we know has to be true? Okay, so negative 3x plus 12 greater than or equal to 0, right? The thing, the expression, so this is f of x, really, right? So when we keep saying f of x has to be greater than or equal to 0, well, f of x in this case is, so negative 3x plus 12 is greater than or equal to 0. Negative 3x is greater than or equal to negative 12, and x, and what do we do now? We flip the inequality because we're dividing by a negative, right? So x is less than or equal to 4. So any number less than 4 is good. 4 is good because it makes it 0, right? Negative 3 times 4 is 12. Negative 12 plus 12 is 0. You go below 4, so you get to 0, then you got 12. As soon as you get into the negative x values, negative 3x is now positive, right? So basically, less than 4, negative 3x is going to be smaller than or equal to 12 in a negative sense, and then it's just going to turn positive. Okay, what do you do for the next one? Same thing. This requires a little different analysis, but so we say, all right, it's a square root function, so the thing under the square root, the function of which I'm taking the square root must be greater than or equal to 0. And we have a little bit of work to do with this. We kind of know what it looks like. It's a parabola, it opens up, blah, blah, blah. What do we have to find? Yeah, we're going to factor this, right? So what I really need to know is, when is 3x squared minus 14x minus 5 equal to 0? Those are my critical numbers. And then, we did this stuff in 20-1, right? Because I know, because we're about to do this stuff in 20-1, like tomorrow. So it's the same idea, right? You can do case analysis, you can do sign analysis, remember all that good stuff, right? Okay, so we want this. So hopefully it's nice and it factors, right? Minus, plus. Okay, so x is negative 1/3, or x is 5. I'm going to sketch that. So I got a negative 1/3, I've got a 5. Which way does it open? Up. Okay, so putting this together with this, what's the answer? To this. This is an aside. And aside. We could name her, so now it's Anne. Okay, but what's the answer? That's not the answer. So what we're asking is, see this graph? Where is this graph positive? when it's less than or equal to negative 1/3 or greater than or equal to 5. Okay, so set of all x such that x is less than or equal to negative 1/3 or x is greater than or equal to 5. Now that's using a graph. I mean, I think that's good enough. Like, I mean, honestly, if that was a negative 3x squared and all of that, then we would just open down and then we would be between, right? But let's take a moment and just say, if we do a case analysis on this, because sometimes we actually have to do that kind of stuff. So a case analysis says if I want this times this to be greater than or equal to 0, then they both have to be greater than or equal to 0. They both have to be positive, which means I need 3x plus 1 is greater than or equal to 0, and x minus 5 is greater than or equal to 0. Okay, when does that occur? Well, so this is 3x is greater than or equal to negative 1, or x is greater than or equal to negative 1/3, and this one is x is greater than or equal to 5. And we take the more restrictive, right? To say if x is greater than or equal to negative 1/3 and x also has to be greater than or equal to 5, then we're just saying this guy, this case results in telling me that x must be greater than or equal to 5. Okay? And that's when I know both of those guys are going to be positive and their product will be greater than or equal to 0. The second case is that 3x, so this would be case 2. This is case 1. Case 2 is that 3x plus 1 is less than or equal to 0, and this is an and, right? That's why we have to go with this, because it's an and. You have to be greater than or equal to negative 1/3 and greater than or equal to 5, which means you have to be greater than or equal to 5. 3x plus 1 is less than or equal to 0, and what about x minus 5? What would it have to be? Right? So either they're both positive, right? How do we get a positive out of a product? They're both positive or they're both negative. Okay. So in this case, this will be x is less than or equal to negative 1/3. In this case will be x is less than or equal to 5. Now we need them both to be true. And the only place that they're both true is when x is less than or equal to negative 1/3. Okay? It's the more restrictive of the two things that are going on here, right? So this, okay, and then these two get put together with this, but I'll accept this, right? So basically, what are you going to do? If it's quadratic, you factor it, you find the roots, you draw a sketch, look, it opens up. I know it opens up, right? It's a positive 3x squared. So it opens up, and I can see where my positive, greater than or equal to 5, less than or equal to negative 1. Okay? Those are like case analysis. There's case analysis. And then there's the sign analysis, and yeah. Algebraically determine the exact value of the coordinates of the invariant points. So what am I giving as an answer? What's my answer going to look like? Would it be numbers? Will it be in parentheses? Okay, it's in parentheses. So this looks to me like the type of question that ends up on a quiz. Hint, I don't know if this type of question ends up on the quiz, but right, it looks like the question that was on the last quiz. Algebraically determine the exact values of the coordinates of the invariant points when f of x is x squared minus 2x minus a is transformed to y equals f of root x. So what do you start off by saying? So invariant points occur when? So invariant points occur when? Invariant points when? Occur when what? Y equals 0 or y equals 1. Okay, so we're going to have to do two solutions, right? We're going to have to say, okay, when y is 0. Okay, let's go here. When y equals 0, then 0 is equal to x squared minus 2x minus 8. We can factor that. X minus 4, x plus 2 equals 0. Don't drop that. That started happening, and we were discussing as to, should we be taking marks off, and we decided to be, merciful. We may be less merciful. So like, don't drop stuff, right? If that's equal to 0, then it's still equal to 0. It doesn't just all of a sudden, you know, it is not out there in space looking like this, right? That cannot become that. So when you're doing written response, do it properly, okay? There will be less mercy. So x is equal to 4, or x is equal to negative 2. Okay, so are we done with that one? No, we have to put them as coordinates. So what are the coordinates? So let's just throw in the coordinates are. I mean, actually, maybe we'll move that down to the bottom. So let's leave that for a moment. But just keep in mind, you don't stop there, right? Like, a lot of people just, oh, look, I can have the coordinates, and that's great, I've got a solution. No. Okay, that's not what they have. And then we say when y equals 1. So then we get x squared minus 2x minus 8 is equal to 1. And this is not going to factor, which means that we have to do what?
Formula.
Quadratic formula. I like to list my a's, b's, and c's just because I know that this does have two distinct real roots, so there are solutions to this, right? You can look at these and say, if there's no solution, you don't necessarily need to go in the quadratic formula. You can just say the discriminant is negative, like just say b squared minus 4ac, work it out, say it's negative, so say, hey, no roots, right? It's like the x squared minus 9 on the quiz. There were no roots there. Or sorry, it was x squared plus 9. Sorry, x squared plus 9, no real roots. There were two non-real roots. Okay, because you can't solve that. You just do it. So then x squared is negative 9, and x, yeah, you can't. Okay, so write down your formula. It's on your formula sheet, or we stuck it on the board. Fill in your values. Minus 4 times 1 times negative 9. And how else do you know? Another way that you know that this has two solutions is it opens up and its y-intercept is negative 9, so it has to dip down below, right? So there are two answers here. And this is 2 times 1. So what do we get? 2 plus or minus 3. So we've got 4 plus 36, which is root 40 over 2. Root 40 is 2 root 10 over 2. Divide out the 2's, so x is equal to 1 plus or minus root 10. I said that as if there was something following that, but it's just 1 plus or minus root 10. Okay, so now we could say the coordinates are 4, 0, and now we can finish that thought. So there are 4 invariant points. Okay. Now you should actually be able to verify this. So, you know, if you finish a test early, then you could graph the original function, and you could, I mean, let's try it. It might blow up, but let's give it a shot. See what we get. Okay, and you only do that when you're done. You do not start checking stuff in the middle of the test. You don't start fixing broken things. If you realize a question is broken, like you broke it, and it's not going to fix itself easily, leave it and go on. Okay, like you might be, then leave what you've got there. You might have been 1.5 out of 2 marks there, but you could spend 10 minutes trying to fix it, and it might not fix. And in the meantime, this 3-mark question on the back page goes unanswered, right? Because you're spending time on, okay? What's your job on the test if you had a job on the test, right? It's to score the highest mark you can. Demonstrate. Okay, what was the actual function? What was the function? It was x squared minus 2x minus 8. So I'm thinking, I think I can do it this way. X squared minus 2x minus 8. Oh, let's just graph that. Da-da-da-da-da. We already knew some of this stuff, right? So I'm going to go here and I'm going to say, give me the square root of y1, which is an alpha f4 y1, right? Give me the square root of y1. See, y1 is already defined. I think this will work. There it is. Okay? Now, invariant points, right? Go into the table. Okay. You're looking for 0, right? So the invariant point is at 4, 0. You're also looking for 1, so we're looking for a 0. It'll go 0, 0, and it'll go 1, 1. Okay. Now we're not going to see the other invariant points, right? Well, we'll see the one at -2 if we go the other way. Okay, -2 has an invariant point. For the other invariant points, we go back to the graph. So we know that in here, the red should be above the blue from there to there, right? Okay, so is that true? So I'm going to do a zoom box. So I'm just going to draw a little box around this. And draw a little box around here. So I'm just going to hit enter and then go out here and down here, and so the red should be above the blue in there when the red draws. Okay, yeah, there it is there. You can't quite see it come down. We know it comes down and hits there, but okay. And then I got an invariant point here, so let's go second calc intersect. The problem with being zoomed out is I have no idea where I am on this thing. Wait, okay, what's root 10 is like 3 something, right? So it'll be like 4 something. And I've also got this thing sitting on there. All right. Okay, I'm going to go zoom standard. I'm going to just put it back. If I want to find the invariant point, I'm better off in a window where I can see what's going on. Come on. Draw. So I'm looking for this guy here. I didn't want that. Second calc, intersect. And 4.16. Quit, and we got 1 plus root 10. It's 4.16. Same one, right? So the only way you're going to do that kind of check is if you have a lot of time at the end. You know, you're finished and you're sitting around and you're saying, I got a lot of time at the end. I can go back and check this stuff.